Okay, so this is from our friend Jacopo Bertolotti. And why don't you tell me what he's demonstrating here?
So this...
I'm gonna bring it a little bit more on screen now that we saw his name. Oh, I'm sorry, you were... I took the explanation of it off screen. Okay, go ahead.
So this is another map of orbits around this central gray spot. It says central forces that decay as 1 over r squared are special, is the guarantee that all bound orbits are going to be closed. It's probably from Bertrand's theorem. Small changes in the power will lead to significantly different kinds of orbits.
Yeah, so what's interesting here is do you notice the black orbit?
Yeah, it's just one closed loop.
That's what the 1 over r squared decay. So he says that's going to be closed. I mean, it is closed.
Yeah, so that's how Newton's version of gravity worked. So if you were 1 unit away from something, gravity would be 1 over 1 squared. If you were 2 units away, so twice as far away, gravity was 1 over 2 squared, so 1/4. Okay. So gravity goes, as you move away from an object, the gravity decreases by the square of your distance.
Okay.
Mm-hmm. And if you have that,
then the orbit will be, it's fine. It's just one loop here, the black one.
It's a nice, stable, closed orbit. But if there's any deviation...
It's just small, like this, the purple one's to 1.9
so
and the orange one's to
smaller.
2.1.
Yeah, so what do you see that's different about those orbits?
So it looks like the loops don't actually close. Like they just kind of keep going around and they're just a little bit different each time. Like this one... Like they're kind of the same sort of shape, the 1.9 and the 2.1, but both of them just don't connect with where you started with.
Yeah. Oh, it also, maybe it's just because this orbit looks smaller, the purple orbit looks smaller, the orange one looks larger, and purple one looks like, the purple object looks like it's moving faster.
Oh, interesting. Okay.
Than the black and orange.
That might just be because the orbit's smaller, so it's a smaller distance to go.
Yeah, that could be.
I don't know what this F is, but it's the same.
That's the F. He's just using F for the force of gravity.
Okay.
The force is that symbol means proportional. Okay. The force is proportional to 1 over r squared. 1 over r to the 1.9, 1 over r to the 2.1.
So it does make sense that if r is 1.9, so if gravity is pulling on you more, so you're dividing by less, then the orbit will be smaller of the force, and if it's slightly less force, then the orbit will become larger.
Yeah, wow, that's great. That's a great observation. That's really good. So now this actually helped me understand something that I hadn't really appreciated before. Or I had heard the story, but I never really understood it. So one of the discoveries, or one of the things that scientists knew was that Mercury's orbit wasn't a perfect ellipse. And they knew this in the early part of the 1900s. Okay. And when Einstein's general relativity came about, it actually explained that discrepancy exactly. And Mercury's orbit is rotating, just like these non-1 over r squared orbits are rotating. And this is the idea that's going on there, because it's not exactly 1 over r squared. In fact, all the planets' orbits are rotating, but you can really, I guess they could only really appreciate it or notice it back then in Mercury's orbit, because that one's so fast.
Okay.
But we're going to look at the code for this, because Jacopo shared his code too, so we're going to take a look at the code and look at it on Mathematica.
All right.